I am incredibly happy to present our next presenter. Zhuo will be joining us and talking about USB device fuzzing without having the devices handy, which is really wonderful because they become clunky to carry around if you got a billion of them. Anyway, thank you so much, and we look forward to hearing your talk.
Hi, I'm Zhuo Ma from China and from Tencent Shenwu Lab. So here I'm gonna talk about my research about the USB device driver fuzzing. In this research, I didn't use any device, real device to get all the bugs. So I'm gonna share my research. And here is the agenda. The first, I'm gonna just quick go through the basic background of the USB protocol and USB devices, and then I'm gonna just give a brief introduction of the USB driver working on the on Windows, and then I'm gonna summarize some previous research on the USB fuzzing and how is some and how we pop up our ideas on this topic. And then I'm gonna talk the most important part is my work and how we achieve the fuzzing, and then the final is some results and a demonstration for the fuzzing system. So sorry, and the USB is a standard. It's most common used interface in the modern PC, even in your mobile devices, and it was called Universal Serial Bus, and it currently have 5 versions. It's 1.0 and 1.1 and 2.0 and 3.0 and 3.1, and basically it have 4 pins for the communication, and the 2 pins is for the source, for the power source of VCC and the GND, and the another 2 pins for the communication for the data transfer, and is D plus and the D minus, and basically USB protocol have four type of transfers, and the first one is control transfer. Control transfer is mostly used in the initial state for the setting up the USB device by operating system, and the second type of transfer is asynchronous. Is mostly common used when you use in the web camera, and because this kind of transfer didn't give you the promise to give you exactly the accurate data, but it will just give you the data at the time you want. And the third one is interrupt transfer. Transfer. This kind of transfer is just give you just small amount of data, but with a very quick response. And the last one is bulk transfer. Bulk transfer is mostly used in your USB flash drive, and it can transfer a large amount of data, and it is stable and reliable. And there are still some four concept in the USB protocol. The first is device, and it defines the roles for the communication. And there are basically they have 2 roles. The first is the device is mostly is the USB device, and the host for the PC, and the host is the initiator of the communication, and the configuration configuration is just to define what kind of the USB you are using, and the interface is define the interface the port for communication, And the last one is the endpoint. Endpoint is the basic element for the USB communication. And so in the protocol, we have two they have defined two IDs to define the unique type of a USB device, and they are a VID is vendor ID and the PID is product ID. And the VID was assigned by USB forum and to the vendor, and the PID is defined by the vendor. So and there are a lot of there are also some classes in the USB protocol. You can define different classes means different function, and generally a USB device is a passive device. You can the device cannot initialize the a communication. It can just accept the request and send the response back. And there are a lot of different classes, and the most common classes where it is a keyboard is HID device, and the web camera is just and a printer is another classes, and the reason why a USB device was common used because it's a plug and play. You can just plug your USB device into the PC, and the system gonna load the driver, and then you can use it. And the progress for USB device to work is defined. We can divide it into 4 phases, and the first phase is we call is enumeration. And in this stage, operating system gonna request some basic information from your USB device, and then use this device to use this information to do some driver selection. And after the operating system find the matching drivers, it will load the drivers and do the initialization. And after that, you can use your USB device. And on Windows, there are some. Here is the progress that Windows to detect the USB device plugged in, and how they enumerate the new device when you plug it in, and the Windows will detect the voltage change between the D minus and the D plus. Once the voltage changed, it means some device was being plugged in. And after that, the kernel will just start the enumeration progress, and then load the class driver. And after the class driver was loading, and the system gonna to do some search the specific driver for this device, and then call the driver's entry point, and then after the initialization, he will notify the user mode that you can use the device. Here is the workflow of how the enumeration work in the hub USB hub driver, and here are the some details and how Windows to search the specific driver for your USB device, and he will spawn a userland process called the driver install, and with the argument, and it takes 3 arguments, and the first is instance ID, and the second is VID and PID. And the VID and the PID is just collected from a USB device, and the instance ID was generated inside the operating system, and it will just use these three arguments to do some LPC calls, and eventually it will go into the Windows update server, and then after that it will get the result for whether they got the drivers or not. And here we can see the three key elements to find the drivers. The first is VID and PID and the instant ID, because the instant ID is checked in locally in the operating system. So we can just reduce the keys for driver searching, and it's VID and PID. VID and PID is just burned into the firmware of a USB device. So here is just emulation for this progress. I wrote some code snap to emulate this progress and to do some research. And so here we come some previous research for how the other talent people to doing the work on USB fuzzing, and the most famous research on USB is the bad USB. But the bad USB is just I think they just simulate HID device, and you can just write some script and put the script file into the internal flash of this bad USB device, and you can just simulate to simulate some keystrokes or the mouse moving like that. But it's not actually it's not kind of a vulnerability exploit. It's just using the exiting HID function to do some malware work. So in 2015, and another guy gave a talk in BlueHat USA and give his talk about USB fuzzing, and also released a tool called Visual USB Fuzzing Framework, and it was basically it's based on the QEMU to do the fuzzing, and but most of his work was doing the fuzzing on the enumeration progress, and the target they want to fuzz is like Linux or Unix, some open source operating system, because it's really easy to monitor the state of kernel. And the third one is someone use the USB in the middle fuzz to interact the USB communication, so you can manipulate the packet of USB communication and change some bit, and that will just trigger some bugs in the operating system. But obviously, this man in the middle fuzzing is really slow because it's depend on the speed of your microcontroller. So and it cannot be you cannot use this kind of fuzzing to be a larger scale because it's costly. And the fourth kind of USB fuzz is they use the Adreno to just simulate some malware malform USB device and to see if any bug is found. So after we reviewed all the research on the USB fuzzing, we pop up our ideas is how about how to do the massive scale fuzzing on closed source OS like Windows. So here we come the target. What we want to fuzz is we want to fuzz the USB drivers that was automatically downloaded from Windows Update Server. And the attack scheme is we plugged a USB device, and then the operating system will search the driver for us from the internet, and then they will download and install and launch the driver, and then our device will trigger the bug inside the driver, and then we pound the target. So after we have this idea, we came up a lot of questions. The first is how many drivers how many drivers can be downloaded and triggered this progress, and how to get all of these drivers, and how to analyze all of these drivers, and what to analyze. So what kind of information to assist our fuzzing, and the most important obstacle is to after we got all the drivers, we cannot trigger let all of these drivers to work because we don't have the hardware. So how to do all the work without the hardware? This is the problem. And the other questions is most old school questions for making a design fuzzing system. So after that, we have to do all the crash analysis and how to exploit the bug. So here we can, before we go forward, let's go see the attacking service of USB. And the first is we can fuzz the enumeration progress, and which has been done by a visual USB fuzz. And the second, we can fuzz the class driver, and the third, we can fuzz the device driver, because we believe Windows has been tested by many hackers, and some built in the class driver or the progress of enumeration will have very few bugs to be found. But the device driver was submitted by the third party developer, and this third party developer will differ from the code qualities, so it will give me a lot of opportunity to find vulnerabilities in these drivers. And all the drivers was signed by Microsoft. So if we can find the drivers, find the bugs in these drivers, we can gain the kernel execution, and so with no doubt. So the first question is how many drivers do we have, and when we came up with these questions, the first action we want to take is just enumerate all the combination of VID and the PIDs, and because from the selection logic of Windows Update driver selection, and it will be only one. If there is drivers, there will be only one drivers will be matched. So let's do some math, and we will find the combination of these numbers is really huge. So we cannot use just directly to just enumerate all the combination of this, and so we we just go forward to see if we can find some valid VID was to just reduce the numbers because VID have maxed to 65 Ks, but not all, most of these numbers haven't been assigned by USB forum. So among all the VIDs, and not all the vendors has submit their corresponding drivers to Microsoft. So if we can find how many VIDs has been how many vendors has been submit their product to Microsoft, we can just reduce this combination numbers dramatically. So here, after we do some research, we found this website, and it's maintained by Microsoft. And if you can just submit some patterns, and you can do some to just get some results, and then you can just write a spider and to do this progress automatically, and then we got about 1,000 valid VID vendors has submit their drivers to Microsoft. But how to get all of these PIDs for each VIDs? So the first we came up with two schemes. The first scheme is just to simulate the progress for driver searching, like I showed before in that picture, and write some code and to do some to just enumerate the PIDs for each VIDs. But yes, I have done it, and I tried it. It's easy coding for one platform, but there are a lot of problem. Is you have to submit the instant ID for the searching, so you have to bypass the instant ID locally. It requests the system privilege, and you will do a lot of work to do this, and you have to hook some code inside the Windows Update server, so to just change some results, and it's not easy, and it's also low efficiency because the searching is low efficiency, and during this approach, I found a memory leak in these servers, and even I do some patch, and it still leaks, and it will crash about in 1,000 tries, and so it's just the result is not reliable, and we can't do it scalably, and actually, if you can, if we have done this progress in just one version, if I want to port the tools to another version, I have to calculate and reverse another offset to hook, and it's a lot of work to do. So we come up the second scheme. We have to make a standalone tool and to just simulate all the progress. But in this we have to reverse all the protocols, and thank you, Microsoft has published the spec document for the protocol, and I just read the document and do some reverse engineering to extract the actual data for synthetic update when doing this communication, and I just change and insert atom of our fake hardware to just pretending we have a new hardware will be inserted in the PC, and then we collect the result and write a client in Python, and we collect all the information, and then here are the results. And this result was I think I done it in 2017. So if you do it now, it will be different, but not too much. And finally, we filter out all the same update ID and the same URL, same download URL, and we got about 4,000 drivers. It's a very huge amount to fuzz and analyze. And after that, we have to analyze all the driver caps to see if we have got any interesting stuff. And roughly, when I do the approach above, I have spider all the catalog, the website, and I spider about 45K drivers and from this website. And what I have to do is to see if any conditions I can reduce the members and to find any target I want to fuzz. And the first is there any system file, driver files exist? Because if the driver cap do not have any system driver files, it's not my target. And the second is how many files, and because some of caps contain many system files, you have to see which drivers will be loaded when the hardware was plugged in. And we have to do some collect basic information like driver type. Is it made by WDM framework or WDF framework? And also we have to filter out if the drivers the caps contain the PID we want. And we also have to do some dynamic analysis of the INF file to see if any copy file action was found. Because if no copy file was found in the app installation progress, it will not contain any effective target we want. So for the further analysis, we want to do some to collect some information from the binary level, because that will be help when we're doing the vulnerability analysis and exploit development. So I developed two systems. The first is to automatically analyze all the cap file. Like we can filter out that all the caps without any system file, and then we pass the INF file, and then get all the dynamic behavior of that. And then I developed an IDA plugin for the binary analysis, and we just to most accurate to determine the type of driver, and then we identify some callbacks or event handler of this, and search some sensitive APIs for to mark it is vulnerable or not, and we also recover some WDF prototype to make the code more readable. And then this is the result for the plugin apply, and the right is just you load your drivers into the IDA, and you give the just like rubbish. You cannot see any useful information. And the right one, we apply the plugin. We recover all the API names and the types and all the structures. And we still don't have hardware, so we cannot prepare all the devices for these thousands of drivers, and if we use it, we cannot do it automatically, and it's also costly because of this. So the solution is to use emulated USB device, and we write the USB protocol in Python, and we install the Windows into VM, and then we can monitor the standards of VM. So here the solution is we use QEMU, and you use USB redirect protocol. And here is the whole picture of a fuzzing system. We generate a VM image for the base image, and then we generate we can generate all each VM depending on your target drivers, and then to put it into the VM pool. And the main control system will just do some work on the fuzzing, and after we got the result, it will just write up the result into the database and collect all the CrashDump to the fuzzing results directly. So here's the introduction of the USB redirect protocol. It was used to redirect your physical USB device into the virtual machine, and if you use it in QEMU, you can just redirect your device into a normal USB a Unix socket. So all you can do is connect to the socket and send the protocol, and then a visual USB device was popped into in your VM. So so that's the keys. And as I mentioned before, back transfer was mostly used in many device drivers, and this transfer transfers a lot of amount of data. So this data often was customized data, and if the driver want to read and pass the data, there will be some bugs. So we add some emulated code in this progress, and to see if we can find something. And so to do some fuzz, and we cannot just fuzz this progress outside the visual machine. We have to fuzz the VM, fuzz the progress. Sometimes we have to run some program inside the VM. So here I used assistant feature is called QEMU guest agent to run the program inside the VM, and it exposed some another Unix socket outside the VM, so it's easy to manage this progress. And in this and the QEMU guest agent provides some function for us to do this. And the first is to probe the VM states standards. But when I trying to use this, is not reliable. And so I came up another solution to overcome this, and I'll mention later. Another core stuff is to do the VM management, and we have to manage the standards of all the VM you are fuzzing, and you have to the initial state is just I installed a raw Windows on the VM and without any other extra program. And after that, I wrote a script to install all the program and all the script and all the files was used to just make a good environment. And then when I want to fuzz a specific drivers, we just install these drivers, pre-install these drivers into the VM to make it quick, and then take a snap of these standards, because it will just speed up the fuzzing progress, and you can just restore the VM snap, and the bottom part is the fuzzing progress, and we plug the visual USB device, and then we monitor the driver standards to see if the drivers is working, and after we ensure the driver is working, and we start the fuzzing progress, and then we can monitor all the standards and to collect the fuzzing result, and after the fuzzing ends, we just to switch to another drivers. Because what we are targeting is to fuzz the drivers automatically download and installed from the Windows AutoUpdate server, but is the download and the installed progress is take quite a long time. So what I did is to just download all the drivers, and then pre-installed all the drivers for in the VM, and that will just to bypass all this progress. And when your visual USB device was plugged in, you can the system will also find this driver and load it into the memory. So that's the and during the installation, we can also analyze some deeper dynamic behavior to just reduce them to find our target. And here the mode of fuzzing, and the first is the plugin fuzzing, and this progress is when you to find the bugs when you just plug your USB device into your PC, and then some code will run, and you will find this kind of bugs, and the bug fuzzing is we just to send some random data when the driver requests some bulk data. So if in that progress, and if we did find some bugs, and the IO control bugs is IO control fuzz is we just launch a program inside the VM, and to just fuzz the interface of the drivers created, and then we we also find some bugs. And here is the designing of of the fuzzer, and we just to automatically dynamically enumerate the device interface that's created by the driver. For this, we just make some. We will take a baseline of the VM we created, and then after that after the USB driver was running, we run the program again, and we get another baseline, and we compare the two results, and then we can just know which device interface was being created by the drivers. And then we do some random fuzzing on the I/O control code, and that's it. So here is the monitor, which we want to monitor. We need to get the fuzzing progress. We need to just recover after the BSOD, and then we need to just to get the crash dump and the test case. So we also need to get the standards of driver loading. And here's it. I used a shared directory to share a large amount of data, and to when the crash happened, and after the reboot, we just run a program to copy the crash dump and the test case into this shared directory, and then we got all the data, because the QEMU guest agent is not reliable. So we just use this kind of way to monitor the alive standards of QEMU. And yeah, this is just summary to what to monitor. And we also developed in the verification to verification of your bugs. So when we find, we also to do the kernel debugging inside the Linux, and this gives us a big opportunity to repeat the bugs and ensure the bugs. And then I also make some script to do the automatic auto-analysis of all the CrashDump I got, and then after that we can just to do some duplication to just reduce the amount we want from the unique crash. And here's the example, and I passed the it shows it can achieve the kernel execution, because the RAX was being changed by overlapped by some random data. So here the result. We got more than 100 CVEs IDs for all the bugs. Yeah, here's the demo. We'll see. Yeah, in the video, I launched about six visual machines at one time, and at this standards, all the VMs was running, and it's just waiting for the visual USB device was be plugged, and so let's wait. And now all the fuzzing system is just to see if any the drivers is running is loading and running. So it's checking the standards of the drivers for each visual machine. And if you see some green line, is just finished. So let's wait. This video is a little bit long, about 2 minutes. So let's wait. Yeah, the driver is loading for the for one more virtual machine, and then it starts fuzzing, start fuzzing the progress, and after that you will see some that. Yeah, it's also print out the progress of fuzzing and into the console. Just yeah, the first BSO, the second, third, the fourth, and the fifth. That's the that's the demo. And so we came up to the summary. In this, we just found a novel attack service for the Windows, and we established a new fuzzing system to find all the bugs without any devices. So yeah, that's it. Thank you.
Thank you. Thank you very much.